All right. But the idea is that shows the screen, not my face. So let's see. Okay. So that's how YouTubers work, huh? So they set up Zoom and you it's already connected there. So close. Should I put my Venmo there too? Yeah, if you want this channel to continue, please subscribe to my Patreon. Right? Okay. Let's see. Okay. Got it. Share screen. Share. Well, this is not what we want. Okay. All right, we're live. All right. Good morning, everybody. Today, we're going to jump to laboratory number 5, which is classification. Okay. And this is a common task. Classification can be done on satellite data, on photograph. I mean, the data that we use doesn't have to be high quality or doesn't have to be of scientific type. Photographic cameras can be classified. Pictures from Google, for example, uses these cars that goes driving through the cities, collecting with this 360 camera, and they classify the front of a house or a business and assign the name of the business to that. So classification can be done in any type of, let's say, digital imagery. Now, in our case, we're going to use satellite data to do that. And the caveat or the challenge here is that we understand the location that image is located. To give you an example, if you are working in the Great Salt Lake area, okay, what sort of major land features exist in the Great Salt Lake area that you can remember from visiting that place? Are there lakes around there? The Great Salt Lake area. All right. Yeah, there is one, right? A very large one and smaller ones. Are there urban areas? Yeah. Are there green areas? In the cities, yes, parks, but also there might be small farms, small farm plots around. What else is there? What else? Buildings, yes. Yeah, man-made structures, very good.
Mining or stuff down there.
Say that again. Mining, yeah. Mining. Okay, so that is giving you already an idea of what sort of classification map we can develop in an image that comes from the Great Salt Lake area. A similar train of thought can be done for any other location like Cache Valley. Cache Valley has forest areas, agricultural areas, urban areas, green urban areas. It has lakes and water courses. Also have some rocks, exposed rocks and exposed soil too. So how many classes an image should have? That's a question for you. How descriptive the image should be? Exactly. Very good. So, for example, let's say the US Department of Agriculture wants to know the total acreage of farmland in Cache Valley. How many classes my image should have? 2. All right, minimum is 2. Ag or not ag land. All right. Now, USDA, and you are the remote sensing expert, and they tell you, oh, you took the remote sensing class and you know Google Earth. Perfect. Okay, I got a job for you. Okay, now I want to know, for every 5 years, I want to know the acreage of the different crops in Cache Valley. How many classes my map has or should have?
Crops.
All right, which is about quite few. It's not over a dozen. Okay, so we have alfalfa and corn and barley, potatoes. What else we have? Oh, we have vineyards. Yeah, we have vineyards. Grapevines. Yeah, this is a nice place if you are planning to get married. It's a nice venue location surrounded by vineyards. Yeah, there is one. What else we have in terms of crops? Corn, yeah, corn. So no more than a dozen. Okay. So on. So the level of classes that we're going to have in an image is going to depend on the information we need to generate from that. Okay. So there are examples, and let me pull one here. The NLCD land cover map. We're going to do a poor mimic of this map. Yep. In the sense that we're going to go through the mechanics of doing a classification of an image. Let me see. NLCD. So the USGS, it's the US Geological Survey Agency, has as a task to provide that sort of map classification every 5 years. But not only about what is farm and what's not, it has to report different levels of classification. Let me see here. Interactive viewer. Okay. This is the products that the USDA, USGS, through the Multi-Resolution Land Characteristic Consortium Group, which is a group of federal and academic organizations, they generate this classification map. So
how did you get to this?
how do I get there? I type in the search NLCD land cover, is the National Land Cover Database. You click on the first option. Okay. From here, I go to the official USGS website for the National Land Cover Database. And it says here NLCD, National Land Cover Database 2019, which is the most recent data. There is no 2022, not 2021. So it's every 5 years or shorter, but it's never like yearly products. Yep. Visit full size. It will send you to this website. Now, it's not very intuitive how to get the data, so just go to this section that says NLCD 2019 data now available. Here at the bottom says interactive viewer. And that's where it'll take you here. Okay. So this is, yeah, go ahead. How do you collect this data? Okay. So we're going to do the exercise of today is to try to replicate this, but not at the level they do. They have over 70 classes in the map. We don't have that much time. okay, to do 70 classes. So we will do 3, okay? But we're going to do it as they do it, okay? So I'm going to show you the procedures, the algorithms, how to validate also that answer, how they know that you are assigning to this pixel to be water. How we are making sure that it's water, okay? So just looking at this image, okay, you can zoom in, try to go to the Gray Salt Lake. So this data is free and available to everybody. Everybody here in the room recognize that blue area is the Gray Salt Lake, okay? So every color here in the map represents a class, a different class. So there are different shades of blue, different shades of green, different shades of brown, and different shades of red. I'm zooming in into probably around Ogden. So the resolution of the data set is 30 meters, our Landsat resolution. Let's see, it should be here. This, in this icon, in this sandwich, I was told this is called a sandwich icon. It opens the legend. Every pixel or every different color pixel is assigned to a different class. So they do this work of visiting the sites, visualizing not only the Landsat image, but also base map images collected by, let's say, companies like Planet or other companies that provide half a meter resolution data. And they do this classification using historical data and develop this classification map. So this is pretty much this is information that city planners can use to see the growth of a city, or USDA, the Department of Agriculture, uses to determine if the production of wheat is going to fall short for the needs of food for the population of the United States or for the typical export amounts. So these sort of maps, these classification maps are very useful. So what we're going to do in this exercise is we're going to focus on 3 classes, how to develop those classes, how to train the algorithms to produce the map, and then we're going to see if our maps truly, the results of our classified map from these different algorithms represent the reality as we know it. Okay? All right, very, very good. All right, so I need you to go to our favorite website, HydroShare, log into the Jupyter Lab, go to the Remote Sensing of Land Surface Laboratory repository and open laboratory number 5. And let me know when you are there. Don't forget to do the pip install Geemap minus capital U to get the
in the terminal.
Yes, in the terminal. Just in case you know, we're live in YouTube today. For real, right? It says here live. Yes, we're live in YouTube. So we're recording this, but there is an option in Zoom that sends it directly to YouTube. So instead of me waiting for Zoom to get the video ready, then downloading it, then uploading it, and then so now let's get it into YouTube directly, right? Maybe I get some followers there, right? Okay. Okay, let me know when you're ready. Okay, you're who's yes, everybody? All right, very good. All right, introduction to classification and regression. What we are looking when we're doing a classification task is that we're going to relate the spectral response in an image to a specific land characteristic. So vegetation, what is the characteristic, the spectral response characteristic of vegetation in an image? What can you tell me about the red, green, blue, and near infrared? How they behave versus soil versus water? Now, I'll give you an example. For vegetation, low in blue, slightly higher on green, low in red, high in near infrared. Okay, all right. What can you tell me about water? In okay, very good. What about the other bands? I need to know how each band behaves.
Blue is the highest.
Yes, very good.
And the rest is the low.
Lower green, lower red, and almost zero infrared. All right. Okay. What can you tell me about soil now? You're becoming experts on this stuff. Okay. Okay. You don't respond. Okay, go.
I'd say it's low in blue, a little higher in green, a little higher in red, and it kind of starts to flatten, but I'd say a little higher in near red too.
Infrared. Okay, very good, very good. All right. What about man-made?
Like concrete.
Yeah. You can type it very quickly right now in the internet and look the spectral response of concrete and tell me. Remember, there is a spectral curve for everything published already. You don't have to guess. Okay? We have internet and we use internet for our research or for our work.
It's pretty flat.
Okay.
Across the board. That's what I'm saying.
Kind of horizontal but low, right?
Yeah.
Okay. Now tell me snow. Describe the major regions to me of snow.
Well, there's lots of reflectance
All
in
right.
the visible spectrum.
All right. High blue, high green, high red. Always near infrared.
No.
This goes down, right? Yes, very good, very good. So everything, as I say, everything has a spectral response. So we are taking advantage of that. The values in the image are going to show, like for snow is going to show values close to 1 in the RGB and lower like 70% or 0.7 for near infrared. That is snow. And if I have vegetation, it's going to be 10% blue, 15% green, 10% red, 50% near infrared. Okay, so already there are differences in the values or in the combination of these 4 bands. So a classification task is to tell the algorithm key locations where we are certain that is vegetation, that is water, that is snow. So we're telling the algorithm, hey, this spatial region that I'm going to give you the coordinates, I'm 100% sure is water. I'm 100% sure this is vegetation, and so on. So you keep building classes. This is 100% concrete. This is 100% bare soil. So I'm asking you, algorithm, to find similar locations that have the similar pattern in the spectral response that are bare soil, vegetation, and water. So that is in a 5 minutes or 2 minute explanation what a classification algorithm does. How many classes do we put? It depends of what are the questions that we are asking for. Are we asking just to know basic characteristics of the land, like water, vegetation, and urban areas and bare soil, or we want to know, like, for example, here, the different shades of red is indicating the different levels of urban development in the area. Like high red is high intensity urban area, that means buildings. The lesser red pixels, those are like townhouses or houses with backyard, that type of urban structures, or let's say stores. So they have different levels of red, even one that is called open space. It's urban area, but it might be a parking lot. Okay, so all right, let's begin our journey to classification. Okay, as we know, let me reset my my map so we start from scratch. Okay, all right, let's run the first cell and we should get a map. Okay. Oh, also I figured out why we have to put so many times the Google Earth Engine key is because Google has decided to reset that key every week.
Oh, really?
So when you go into the process that, remember, we open homework 118 and we get that link and we go at the very bottom of it, it says, hey, we will reset this code every week. So that's what happened with us. So for example, if tomorrow you try to do the homework, the key is there. But the closer you get to the next Friday, that key is invalid. So it's a Google thing. It wasn't the HydroShare thing. I was thinking they were, and I was wrong. But it's fine. Okay. All right. Did everybody got their map, or you are still updating your Geemap? You're good? Okay. The example tends to do this in San Francisco, but let's do it for the Great Salt Lake. So how do we get a coordinate for the Salt Lake City? One way is to navigate through your map. Okay. And zooming into your map. Okay, I'm about Antelope Island State Park. So to get the coordinate for this location, I'm going to go to the wrench icon, going to click the eye of inspector and click on Antelope Island State Park. And it's going to give me a point there, the longitude and latitude.
Sorry.
Okay. Let me turn off. Okay. Okay. So I'm going to click on Antelope Island State Park. But first I need to click on the eye of inspector, then click here, and I should be getting there. That's the point. So I need that number for the next cell. In the next cell, we're asked for a coordinate. So we're going to use this coordinate for that. Okay. $41.043. Okay. Once you got that point, run that cell. It's going to call Landsat 8. Landsat 8 is going to sort it by cloud cover and select the visible bands. Once you run that cell, run the next cell to see the image.
Trying to activate.
Okay.
I try to activate my propellers engine from the Python script, but there's use one thing.
Yes. Try 180. Okay. You should get a similar image like I'm getting there. But is this? Let me see. So this is somewhere else, right? This is San Francisco. Why is doing San Francisco here? Why you're doing San Francisco?
Imperial latitude is to be negative 112 instead of 122.
112, right? Okay. There you go. There you go. Now, our beautiful Great Salt Lake. Okay. You got a similar image than me? Okay, very good. Okay, what have we learned about reading a false color map? What is intense red? Intense red. What are that? What type of surface? What type of is?
Vegetation.
Yes, very good. Dark blue. Water, okay. Bright spots.
Salt.
Salt, bare soil. Okay, very good. What about, but we have a city area here. We're in Ogden already. So let's zoom in into the Ogden area. There we go. Okay. Okay. What we're looking now is an urban setting. Why there is so much red?
Landscape.
Grass and landscape.
Yeah, backyards, front yards, parks. So it's different. But if we, let's see, let me hide this part. And where is my icon here? I'm already in UrbanNet settings, and I have clear indications of green urban areas. But if I activate my layer, so our job is to transform this image in many classes, as many as we can. Well, let's start with 3, okay? The first thing that we need to know, and for classification, is to have a relative good, not that profound, but a relative good understanding of what the different features mean. Okay, so that means because we are local, we know that this is a lake. Despite the change in blue hue or tint, we know that that's water and this is water. This is the Bear River Refuge, right? I think. And there is another pot of water there. So let's see what the code is asking us for the first class. Well, it's telling me, okay, I have the false color image, but I could use vegetation indexes to help me with this task. Okay, it's good to have an additional layer of information. So let's calculate NDVI and let's add it to the map.
I have a question about that.
Yes.
When we were talking about assessing the vegetation on like earlier this week,
Yes.
I thought we decided that NDVI really only works for like green and yellow leaves to see like plant health.
Yes, green and yellow leaf. Yes.
So why can we use it in this case for like everything, even like urban areas? And
Well, it's going to depend, and that's a very good question. Very, very good. Let's see. In this case, what we should have done is to avoid the senescent period of the leaves and just pick up a region where we know or we're familiar with that forest leaves and agricultural leaf are green. That's good. So for example, here where we do our query of Landsat, we could have chosen from May to July, a shorter period. We know that September, October is when we see the yellowing and the or the senescence of leaves, and we could have avoided that. But that's a really good point. So let's do that.
So, are we using NDVI to also like differentiate urban areas too? Like, is it
We can try.
okay? 'Cause I'm just thinking that's like what it's doing.
Yes.
Maybe not understand.
Yes. So let's see. Let's put from May to July. So let's start from the top. How you start from the top? You can go to kernel, restart kernel, and clear our outputs. That will restart the worksheet.
Have you changed the date to
Yes, from May to July. That's a really good observation. And that's what, for example, when you got those naive images from USDA, those 1 meter resolution naive data, they also choose a period in the year where vegetation is still green. They avoid late season flights because of that.
maybe it's doing every year or
No, it's every 3 to 5 years. Okay, we got a map. Okay, then let's calculate now with more confidence NDVI. So you will notice that this time I use Geemap function called add color bar branca, it's called. And what it will do, it will add a color bar for your vegetation index. And I choose this color bar. I selected these colors here. I say the minimum value that I want to plot is minus 0.2 NDVI to a maximum of 1. And I'm going to start at blue, then white, brown, yellow. So this is 0.2 and this is 1. So this is about 0. This is 0.2, 0.4, 6, 8, and 1. Okay, so it's giving me a scale of the values for the vegetation index. So that helped me read this image. Okay, so basically, if I'm having very low negative values of NDVI close to 0, we see that NDVI is picking up very well the water area. Okay, close to 0, I have these white spots are around the Great Salt Lake that are bare soil. And this could be bare soil with salts. This could be the salt flats. And after that, I have higher values of reflectance, but that doesn't mean there is vegetation. We start looking at vegetation around 0.4, which is the transition between yellow and green. And it's picking up quite well that agricultural area over there, forest areas here and there and there. And then we have the city area here in Ogden, okay, is picking up a lot of green, implying that there is significant component in that urban area of green areas. Right? Is this part clear? How NDVI is described in this landscape?
So why is the lake at 1 on the southern half of the lake?
Sorry,
Shouldn't that also be, shouldn't the southern part of the lake also be near 0?
let's see. Let's check it. Good question. Okay, here I have the values of the it says none.
Okay.
So it's having very hard time calculating NDVI because of the denominator, the two values, the red and the near infrared are very close to 0.
Okay.
Okay, so it's just an artifact in this case. All right. Nevertheless, this is helpful, and it's good that you ask questions, because that's because
the coordinate that should be like in around 6 exactly.
I change it to this value.
Yeah, I did too. What is the done to that?
Let me see. Yes. Okay. All right. So we have the NDVI. Now let's we have the NDVI. Now the next step, now that we have our false color image, or we can have an RGB image and a vegetation index for support. Okay. Now we're going to build these areas where we have 100% confidence, okay, that that they represent a class. So first, we're going to do this. We're going to define an area that is bare soil. So we're going to use 3 classes, and let's see if we have time to add a 4th class. So the first class is bare soil. Okay. In the past, we were able to draw a polygon with Geemap, but nowadays we have to create a polygon. So you can comment this line and activate the polygon lines. We're going to replace these coordinates with coordinates around in the image that represent, or we believe, is bare soil. Okay, how we do that? Let's go to our image. And just to make sure, we're going to query this light brown area to make sure that they fall within the expected range of NDVI. Zero 0.06. 0.01, 0.2. Okay, they do fall within our expected range of NDVI values that represent bare soil. So what I'm going to do now, I'm going to draw a polygon. Okay, no, not draw a polygon. I'm going to query coordinates that encompass a region that I'm going to use to define an area that I'm going to tell the algorithm this is bare soil. So imagine a square. Okay, so go top left, top right, bottom left. So do a rotated circle. So you click here, you see the value there, and type that value in in the coordinates. Going to put $41, $4.
Cannot make all polygons 2 points.
Say that again.
If you have just 2 points of them.
The code, as it is asking you for a polygon. Okay, but there is an option to draw a rectangle or draw a circle. So in this case, we are using just a generic polygon.
Standards of finding ways and methods to steal money.
Okay. Okay, here are my coordinates. Okay, I try to draw a square, and the following lines will add that polygon to your map. So we can refine the polygon if we need it. So once you complete your 4 coordinates, run that cell. So in my case, I made a mistake, I think, because my polygon was supposed to be small, but it's drawing something very, very large. So the coordinate here is good, here is good.
Your last coordinate.
My
was
first
32.
coordinate is wrong. Yeah, 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 okay. So, okay. This is too high. Let me see. No, the latitude is okay. Is the last one?
I think, yeah, the last one is
Oh, 41. Okay.
Also, I'm getting an invalid syntax.
Okay, just give me a sec. Okay. Much better. Okay, you should have gotten something like this. Okay.
You could just put it in next one.
Says verso. Let me see. Okay. If you are ready, you can move with the next one. The next one, command the polygon map user and activate the second polygon and pick up coordinates now for water.
Can you say what orders the points need to go in again?
Say that again.
Top right.
Top left, top right, bottom left. Okay. Sure. Oh, you didn't.
Oh,
So everything is
why.
commented.
Gotcha.
Yeah.
There we go.
Everything's-
For vegetables or for vegetables?
Now it's for vegetation. Okay. And once you're done for vegetation, do it for water. Isn't this fun? Yeah. Go ahead.
I see there's two for water. Is that just?
Oh yeah, the previous example last year there wasn't many water features, so I added more.
I
So
didn't know if it was like,
no,
with the Salt Lake, you
You-
kind of get that differentiation.
you can actually that's a good approach. We can use one polygon for the dark blue region or the southern part of the lake and another polygon of water for the northern part.
How would you do this? And then maybe we'll get to this, I don't know. If there's like mixed, like you're trying to get different plant species,
Uh-huh.
they're mixed
Yes.
together, how would you separate those? Because you've got polygons.
Yeah, right now it's 30 meters. Everything is mixed in 100 feet by 100 feet. So when you need to go finer, you need better data.
Okay.
Like you go to drone level, planet level, like 3-meter resolution data. And then you have like the coordinates per tree.
Right.
And you draw a tiny polygon, or you just have the GPS and draw a buffer, like a 1-meter buffer around that GPS dot and assign it a class.
That makes sense.
And then you've already got like a collection as well. That kind of have those values there. You don't know.
You had a question? Okay. All right. I should be going because you're going to finish this exercise faster than I, which is good. I'm not complaining. I'm happy when the students do better things than I. Okay.
Where did you draw your box for vegetation?
Southern. Oh, sorry. I draw it for water. Man, my mistake.
Yeah, I did the same thing. I just copied.
Yep. Okay, I need to copy all of this for water.
Is it wrong to, when I did with waters, I just had a box covering both the northern and the southern arm? Okay.
That's okay. Okay. Okay, I did water here. Okay. Okay, now I need to do vegetation. Vegetation. For vegetation, it's important that you try to find the area as homogeneous as possible. Okay. For example, in the urban area, we have urban or man-made material and vegetation. It's a mixed area. So when you draw these areas of interest or classes, locations, you are telling the algorithm, I'm 100% sure this is pure water. pure soil. So when you do vegetation, look in the image where you have the most homogeneous vegetation area, okay? Which might be the upper corner vegetation, the left, right, upper section of the image. So, but you can choose any area that you have vegetation, but as long as homogeneous within your polygon. Okay. So vegetation. I'll be back in a sec. Okay. All right. Who got the three classes in there? Water, vegetation, and bare soil. Very good. Now we're ready to continue. Okay. Now let's right now we have just been building polygons, right? But we need to tell to the algorithm which class are we entering. Is it bare soil? Is it water? Is it vegetation? Is it man-made? So let's read the code for bare soil. We draw a polygon. We're going to tell that to the algorithm that this is bare soil. This is the coordinates, and the algorithm doesn't read text. The algorithm works with numbers. So we're going to assign a class. Okay, so those pixels within the polygon of bare soil we're going to say that they have a class number. It could be a class 1, 2, 3, 100, 101, 1000, but it has to be unique. For every class, we have to assign one value that is unrepeated. So in this case, we're saying this is class 2. Okay, and for purpose of display, we're going to call it bare soil. And now we plot that. We're plotting that polygon. Let's see what class we assign it for vegetation. For vegetation, if we read that line, we have for polygon, we're assigning to a variable called vegetation, but we're assigning class 1. Okay, so I could have called it bare soil class 1, vegetation class 2. It is an arbitrary number. It doesn't matter which go first, second, or third, as long they're unique. Okay, so call vegetation, and water is in this case class 0. In Python, the sequence of numbers start at 0, so we're assigning water to be the very first class. So we have class 0, 1, and 2. Water is 0, vegetation is 1, bare soil is 2. Okay, so now that we have our three classes, okay, and we have a second polygon here that, if time allows us, we're going to build this class to be urban area. Okay, so for now, comment this cell that says for water again. Just comment it.
What's the shortcut to balancing it all?
Control forward slash.
Okay.
Okay. So here is where we're going to combine all the features. We draw 3 polygons, water, vegetation, soil, and we're not using water 1. We just commented. So deleting that water 1 from this list. Okay, just leave it that way, run that line. And let's look at the bands of Landsat that we're going to use. Landsat 8 has coastal blue, blue, green, red, near infrared, shortwave 1, shortwave 2. So this is red, no, this is blue, green, red, near infrared, shortwave band 1, shortwave band 2. So we're basically describing the spectral response of every spot or every polygon we are selecting, and with the same information, it will try to assign a class to every location. So let's run that cell too.
So you always want to use all these bands?
You want to use always spectral bands for classification. The more, the better. I mean, especially if they are different.
Yeah.
Like if you have multiple blues, like in a hyperspectral camera, you have like 10 blue bands. It's too much blue information. You might want to choose one of every major spectral range. Okay, let's run the print. So it's not the best format to describe, but it say that here we're going to use our data, our polygons, and our classes as training information. It's a polygon that has these coordinates. It has an ID of 0, which is water. Okay? So the same, if we're getting only the information for the first class. So in the second is vegetation, in the third is bare soil. So now that we have our data ready, what we need to do now is we need to tell Google Earth Engine to use our polygons to extract the pixels inside every region we draw, and to every pixel, give it the class we defined for that location. So we run this cell. A second part. When we do any regression or classification analysis, especially if it's non-linear, when you do these linear regressions in Excel, you use basically all the data, right? If you have 10 points, you put all the 10 points to do the regression. And that's okay, because it comes from a statistical equation, okay? But when you do this sort of analysis classification, you need to take part of your data to be used for testing. Part of it will be used for training the algorithm, and what is left will be used to validate if your model is actually predicting vegetation where you said it was vegetation. So this section that says randomly split the data into 60% of the pixels for training, 40% for testing, is doing that. For every class, it will separate in those proportions for training and for testing. Let's run that cell. Okay. Let's see. There we go. Now, what algorithm Google Earth Engine or any other software that does remote sensing is going to use? Well, that's the thing. There are many. These are the few ones that Google Earth Engine has. Decision tree, maximum entropy, support vector machine. This is Euclidean's classification type. Card, which is similar, like developing a separation of the data, like in branches of a tree. Naive Bayes looks for probabilities. If the values of the different bands look like the values of vegetation, I will say is vegetation. But from a probabilistic point of view, random forest is another version of a classification tree, but instead of using like a single tree, it uses a forest, many trees to. And this uses a spectral region type of information and measure the difference between the red, green, blue values with the pixel that is unknown to assign a class. So the most popular ones are going to be, let's see, a smile card, random forest, and support vector machines. So we're going to run 3 classification models and we are going to check how well they perform. Okay. So let's keep running. Where are we here? Let's run the smile card. And now let's ask for the map. If your image is not centered so you can see if this algorithm did a good job or not. All right. Okay. Visual assessment. What do you think? Is it a good classification? Blue is water, yellow is bare soil, green is vegetation.
Maybe it's too much.
Is it vegetation that in the image, all the green area is vegetation?
Probably more bare soil.
Yep. So let's see. Yeah. Right. So what it's telling me is, well, it seems that it's doing a good job for water. Okay. But for bare soil and vegetation, it's under predicting bare soil, over predicting vegetation. Okay, good. Now let's try the next algorithm, random forest. Let's run that cell and the next one so we get the results. Now, how many polygons should you add? Well, there is no limit. We added 1 polygon per class, right? But in the type of USGS land use classification map, they can use per class, probably up to 30 polygons, 30 to 50 per class. And they have 70 classes. So is because they are running for the entire US. So the forest in Florida behave differently than the forest in Utah. So we need samples from all these forest types to feed the algorithm. Okay. We got results for the random forest. What do you think? Better or worst?
Got more water.
We got more water. Okay, let's see. Let's go to the icon. First, let's compare it against the NDVI. So let's see. Still, there are issues in the vegetation and bare soil. Okay.
Yeah, I think some of the like mountain ranges, the water.
Yeah, it's missing some water spots. Now let's try the support vector machine. Okay. Let's see. You might have slightly different results or different results because you choose different polygons, right? So, okay, what do you think? Support vector machine this time.
Is there any limitation for the number of input that we consider for our machine? Is there any limitation for the number of? Like here you like some parts, so we can also consider like NDVI, I think.
We could, but in this case, we're keeping it simple, but we could have included vegetation indexes as well. Okay, we're seeing that the support vector classification does a slightly better job on describing bare soil, but still we're having issues on the classification map. So these maps are not ready to be shared with the public or with the end users of it. Issues. Well, how we solve these issues? Okay, so the idea to solve these issues is that if you see an area that is misclassified, let me okay. Let's say this area around here where my mouse is, okay? Come on. Okay. In those areas where you see the NDVI and the class are different, those are the areas where you create a new polygon. So the areas where the resulting class, like it's same vegetation, but you see the NDVI and it's bare soil, you create a new polygon for bare soil. So now the algorithm knows that that area has to be bare soil. So we have a second polygon for water, right? That we didn't use. So let's create a polygon of bare soil where the maps are saying is vegetation. Okay, this is going to be okay. Let me know when you are done selecting your points. Okay. Because we need to do a small change here in the bottom lines of codes. Done? Done, everybody? Okay. So we need to enter this polygon as a bare soil. Okay. Let's uncomment these cells. And what class was bare soil? 0, 1, or 2? 2. So we need to change that to 2. And in the front, to avoid errors, bare soil soil 1. And here we're going map at layer. We need to use the name of the variable. One. And we'll call it bare soil 1. Okay. Once you do that, those modifications, here it has to be called bare soil 1. Okay. Class 2.
Fill color yellow, maybe?
Oh, yellow, yeah. That's true. Okay. Class 2, bare name, bare soil. And let's run that cell. It should show a polygon where you selected. Okay. So now here in the section that says training features, we need to add one more that's called bare soil 1. So that's how you add more polygons. We created a new polygon, we gave it the same class, and here, when we combine all the polygons, here we add that new polygon. It can have water 1, water 2, water 3, vegetation 1, 2, and 3, and so on. Okay, let's run this cell again. Okay, let's run the following cells.
If we have polygon, we can upload it.
In case you have polygon, there is a Geemap tutorial on how to upload your own shapefiles. Okay, let's keep running here until the splitting 60 for training. Pass the nonlinear functions. We need to rerun because everything was already organized and we are adding this new polygon to it. Okay. Okay. Now we are in the smile cart. We can run it and see what's the type of prediction it will make. Okay. It worked, right? So now all this area is now bare soil. Okay, so right. So more polygons in areas where so we defined first polygons for the 3 major classes. We found initial errors. On those error spots, we put more polygons. That helps the model to improve the classification. What do you think? Way better. Can be refined? Yeah, it seems that the forest areas are still too big. Okay, so we can compare it against the NDVI, but it's much better just with adding one more polygon. Yeah. Yep, it's that. Don't add anywhere. Add where the model make an error. That's where you add the additional polygons. So I can come on. Okay. Okay, NDVI. Yeah, now it looks more like the NDVI. Okay, could use a bit more of refinement, but I will say we're like 80% good classification now. All right, just by adding one more polygon. Okay, now let's try it random forest. Okay. Okay, that's random forest. It has also improved. Let's see. This is with the previous with cart. The differences are minimal. So look at the water here. So probably that will be my next polygon to refine water. Okay, so classification is not just one time you dump your data in, okay, I'm good. It's an iterative process. You visually assess, compare against a map that you know the character like NDVI, and then you start doing this visual comparison until you are satisfied with the result. You keep adding classes or polygons to the different classes until it describes as you are looking for. Okay, let's look now at support vector machine. That's when you get that one of your polygons is too big. So when you get an error that says maximum memory, shrink your polygon. So now that we have a somewhat decent classification map, it's time to look at the statistics, numbers. Visual assessment is good, but in the paper you cannot do it look good, right? We need to put a number or a statistic that we can refer to. Okay. Yeah, look, a support vector machine also looks cleaner. Okay. So all three models improve by adding one more polygon. Okay. Accuracy assessment. Well, visually, it has to reflect what you perceive in the image based on your knowledge of remote sensing. But also we have to develop a statistic. And for classification, is called a confusion matrix. A confusion matrix is going to draw a table where in the horizontal lines are your different classes, water, soil, vegetation. And on the vertical, you're going to have columns of the image that says water, soil, bare soil, and vegetation. And it's going to count how many true bare soils or location you say pixels in the regions that you said is bare soil. Actually, the model actually said, or the model classifies them as bare soil. Like if you had 100 bare soils in your polygons, the map could say 50. The value in the intersection is going to say 50. And the other 50 will be in water and vegetation. So it's a way to see how much misclassification happened in your image. So let's see how the card model behaved. We run this cell, done, and we need to get our error matrix. Okay. Okay. So here is water, vegetation, soil, water, vegetation, soil. It says that for water, we have 13,800 pixels labeled as water, and all of them were classified by the algorithm as water, 100% matching water features on water classification. For vegetation, we had, my polygon was smaller, and we had the number of pixels was the sum of this and this value, and I had 21 of them being classified as soil. So I could do as an improvement, adding more vegetation polygons to minimize this error here. And in bare soil, we have the sum of these two. I have 32,000 pixels that in my two bare soil polygons, only 6 of them were classified as vegetation. So the algorithm was really good at this. I probably need to add an additional polygon for vegetation because the sizes of the polygons should be kind of the same. In this case, because we do it manually, our polygons were smaller or larger. So I might increase the polygons. I might add more polygons for vegetation to make this the number of pixels similar to the other classes. Overall accuracy, almost 100% accuracy.
Just to make sure I'm understanding this right.
Yeah.
So that bottom row matrix is saying in the bare soil polygon you drew,
Yes,
6 pixels within that polygon.
were classified as vegetation.
Okay. And then on the second line, vegetation, 51 pixels. was
21 were classified as soil.
Okay.
Okay, so it's showing us where are the fails of the model. What we look is the diagonal, and we prefer that the sides of the matrix are 0. It's never going to be perfect, But if, for example, in this case, I have almost 33,000 pixels, and only 6 were mislabeled. So it's a very small percentage that were mislabeled as vegetation. Okay, so this part I will focus less. Water, we're doing a really good job. I will focus my efforts on vegetation. One, because the number of pixels is very small. I'll need to bring this number of pixels up, similar to the sizes of the other two. Okay, so a kappa value is like the R square for regression. It's very high. It's telling me that our classification has a good quality or has a good relationship between the classes that we define it and the result we're getting from the machine. The same we can do for the random forest.
While that's loading, what is how do you know which regression model to use? How do you know which regression model to use in your?
In this, here in the statistics, if a model performs less than the others, you always use several of them. Okay, here we're testing 3 with the same data, and you start discarding the ones that has less performance.
Okay.
So there is no favorite one that says use always random forest. So you want to use, because all the models use the same data, you can use 3 or 5, and looking at the statistics, you start throwing things out. Okay, look, here in the random forest, again, really good job on water. 11 pixels of vegetation were classified as bare soil, and only 4 were classified as vegetation in the bare soil region. Again, an overall accuracy of 100%. So the models, because we improve it, adding that additional polygon, all of them are giving us good results. So, but this validation is only over the polygon. Remember, we split the data into 60% for training, 40% for testing. To ensure that these numbers are more confident, the more polygons we add, the more split we can have, more 60 for training, more 40 for testing, and these numbers might go down a little bit. So again, this is working well. At this point, just comparing these two models, both of them are good. Okay, so it's our visual assessment where we see water features, urban features, agricultural settings is where we see, okay, I see a problem here in the classification. I might want to add an additional polygon here, an additional class. And here, this is the support vector machine. We have a larger misclassification of vegetation into bare soil and a perfect classification of bare soil and water. So for this small example, the support vector machine is giving us a better classification scheme based on the data we gave. Fine?
Yeah.
All right. Okay, the bonus part. All learning machines are not like the linear regression machines. Like in the linear regression, you define your X, your Y, you throw it into Excel, you get your regression and your coefficients for your linear equation, right? In machine learning, these algorithms are non-linear algorithms. And internally, they have parameters that if you change them a bit, the classification improves. So far, we have worked with default values of these internal parameters. Nevertheless, there is a way to test for the same data, training and the image, to see if the statistics improve if we change those parameters. So that bonus section, the hyperparameter tuning, in the first one, in the random forest, is going to look to change the number of trees that the model is using. Maybe that improve the statistics. Let's see. We run it. What it's doing is what we did before is going to do it 20 times, changing that internal hyperparameter. Because our values are already the 0.99, any improvement is going to be very small. But let's see how it ends up. Oh, got an error. Oh, too much memory. Okay. Will it allow me to do up to 5? There we go. Okay.
What did you change?
I changed the number of trees. So initially I had at 1 tree. If I add 2 trees, it decreases a little bit. But if I put 4 trees in the model, it improved. The classification or the errors that are, we found are decreased if I change the hyperparameter to 4. So where is that 4 parameter? If you go back in the code to the trees, where is that? Here, SVM, no, here. I use 13. If I change this value to 4, it will improve so that tuning, that change of this internal parameter of the algorithm can help to further increase your accuracy of your classification. The same can be done for the support vector machine. Let's see if it runs. It's taking a bit. The same happens in the code for a smile card for the first assignment. Let's see if it finish, but I'm going to leave you a homework that now instead of doing it for the Grayson Lake, you'll do it for Bear Lake. Same job. 3 classes, you can add a 4th class if you want. The idea is to reach a kappa or accuracy classification over 90%. We got here 99 in all classes, but in the first, before we added the polygon, probably our classification was below 70. So you will need to add polygons if necessary to reach 90% or higher classification accuracy. Okay, so that will be all for today, unless you want to wait for this to end. Okay, but if you need to go, that's it for today. All right, thank you for your time. Let's see, it's running.
When you got the error with the random forest tuning, what did you change there?
Oh yeah, so remember here, random forest, right?
Yeah.
So what I'm tuning is the kappa value, this overall assessment of the model. So for every value from 1 to 5, I'm calculating a new kappa. Okay. So, and that's what I'm plotting here. The vertical axis is the kappa values. So if you put a random forest of 1, you get this value of random forest of 2. In the case of random forest, the changes of 3 are like 1 or 2. You cannot have like half a 3, a quarter of a 3. Okay, but in support vector machine, it can be decimals. The gamma or the internal parameters called gamma, it can be decimals.
Okay. And when there's a user memory limit exceeded, what did you do?
Oh, when I got that one, because I had here until this value, the sequence from 1 to 20.
Yeah, that
So I reduced it to 5.
still breaking my five.
Maybe the polygon size is still pretty big.
Yeah, they were actually pretty good. So
Mm.
that's probably why.
I made my buffers around the point, like, once I selected,
Uh-huh.
and I had to get down to 2 400 buffers. So I think it was about the same.
Yeah, that might help. Yeah. Okay, let's see if it finished. Yay, it finished. Look. It's saying that if I use a gamma, I evaluate up to 16, my kappa value increases from 0.898 to 0.994. So where I change that value, the gamma value, I go back to the code where the model for random for here, gamma value, I use a 0.1, but the figure is telling me 0.16. I change that value, my classification will improve a little bit more. All right. All right. Thank you very much, guys. Have a good weekend.
Can you use those models for areas that don't have such obvious bare soil, vegetation, and water?
What do you mean?
Like the area we were looking at is like very large clear areas where there's bare soil.
Yes.
Water.
Uh-huh.
vegetation, like if
Yes.
you're looking at like a city or something.
Yeah.
Where there's not necessarily like a huge area of bare soil.
Mhm.
Can you take a model that was trained in Salt Lake and apply it to like Western areas?
It could work
Yeah,
but every region is slightly different.
so it's better to train it for that specific.
Yeah, I mean, you can, like, let's say, to this classification, bring an image from Florida, for example, and ask to classify. But when you check the NDVI of that image in Florida, you're going to see, yeah. So every location is slightly different, and it requires local points. The USGS collects polygons all across the US, and when they're processed in Florida, they use the points or the regions
Yeah.
for Florida.
Makes sense.
Mhm.
Okay.
Could you train it with just a lot of little polygons?
Oh yeah, yeah.
Like if there's no big.
If there are no big, you can like have a dot, okay, and have a radius of, let's say, 10 meters. So that's within a Landsat pixel, right? So you
Yeah.
can have hundreds of dots that you know are, but the thing is to label them, each of them,
Yeah.
because you can have 100, but now you have to take like 40 of them and say these are bare soil, the others. So that manual process might be time consuming.
So we can have index point data and make a buffer around it.
Yeah.
Go and just save it and then upload it here and do vision.
Yeah.
Thank you.
Mhm. Visual. Oh. Well.